Hey y'all, welcome to Archive Dives with Oxen AI, where every week we dive into interesting research papers and tease out the key insights that you can apply to your own work. This week is a fun half archive, half practical dive where we're going to be going into the era of 1-bit LLMs paper. All large language models are in 1.58 bits. This is a super interesting paper that came out of Microsoft Research a few months ago, and there's actually been some recent code that was released, and we'll be going through taking a base BitNet model, fine tuning it on our own data, and just like diving into the nitty gritty details of how all of this works. So, with that said, let's dive right in. So, like I said, this paper goes into BitNet 1.58, where every single parameter is either a -1, a 0, or a 1. So, there was an original BitNet paper that trained a transformer to have its weights be either -1 or 1. This one extends that work to add the 0 in there, so really it's a ternary representation. And what's cool is this model matches precision or matches a full precision transformer performance with the same model size in terms of training tokens used. So they measure that with a few different tasks. PPL stands for perplexity. And remember, perplexity is like when you're predicting the next word in a sentence, a measure of how perplexed the model is while you're predicting that next token. And so the lower the better, the less perplexed the better. And they released three different models. They released a 7 million parameter one, a 1.3 billion parameter one, and a 3 billion parameter. And recently, there's been some reproductions of the paper and benchmarking, and you can see very on par with the floating point representation versus the 1.58 BitNet representation. So pretty exciting, cutting edge research, and we're going to dive into how it all works. But before we get started, probably wondering why it's called BitNet 1.58 and not just BitNet or BitNet 3 because it's ternary. And the reason for that is in an information theory perspective. If you have 0, -1, and 1, that's a ternary representation. And if you simply take log base 2 of x, that gives you 1.58. So that's why they call it 1.58 BitNet instead of just BitNet. But why should we care in general? Why is this important research, or why is it exciting? And the main reason this is a big deal is it has significant implications for latency, memory, and throughput, as well as energy consumption, which is a function of all of these three things for these large language models running in production. So large language models and transformers are built on top of massive matrix multiplications, and these operations are expensive and require specialized hardware like GPUs to run in production. So in theory, if we can get these models to run on binary or ternary representations, we can run them for much faster and much cheaper. And who here wouldn't like a faster LLM that they could eventually run locally or run in production for their product and not have to call out to an external API? This BitNet research really unlocks the possibilities there. So really looking forward to what we see in the future with these types of models. So before we dive into any code, it'd be great to do a little baseline understanding of the math and like why this all works and why it's exciting at the low level detail of ones and zeros. So if you're familiar with a traditional neural network, you're going to have all of your weights stored as floating point numbers. And what we want to do here with a BitNet is instead of having your weights stored as floating point numbers, have them as 1, -1, and 0, the three ternary representation that we talked about before. And the implications for this is, if you're familiar with matrix multiplication, usually you do a multiplication step and then an addition step. But if you had all of your weights as a 1, -1, or 0, now you can think of it as each one of your multiplications could be changed to just a simple identity function, a flipping of a sign, or a zeroing out. And then the addition step afterwards is now uh, just addition and no multiplication. And you're doing this all on integers instead of floats. So there's just like a lot of computation that you save here and potential for running this on specialized hardware or just doing SIMD operations and more efficient operations on a CPU and not having to offload this to a GPU. So the basic math is you can get rid of this multiplication, then addition, and just replace it with an addition itself. So this is a form of quantization. There's a lot of other work on quantization, and this isn't even the first time that people have been trying to do these binary representations for neural networks. Been working in the field for a long time, and back in 2013 through 2015, we were trying to do a similar technique to binarize the embeddings with convnets or just traditional feed-forward neural networks, and this allows for things like really efficient vector search across, say you had embeddings of a billion images and you wanted to run a nearest neighbor search all on CPU. This type of binarization makes the SIMD operations, simultaneous instructions, multiple data operations work really efficiently on CPUs. So not a new idea, just kind of applied to transformers now that that's the main model that's seeing a lot of traction today. And what's interesting is you can do this quantization, and many people do, after a model is trained. So you might be familiar with libraries such as GGML or Llama CPP. These libraries do the quantization after the fact. And the problem with this can decrease model performance in terms of accuracy because you're kind of truncating the level of detail that was represented in these matrices before. And so the whole goal of this paper is for the neural network to learn its representations to be very close to 1, -1, or 0, and then use -1, 1, or 0 for the forward pass so that we don't get that degradation in performance when we do the quantization. So with that being said, let's dive on into the BitNet architecture itself. So like I said, BitNet sits on top of a transformer architecture. We won't really go into transformers here. If you're curious, just go to Oxen AI/blog. We have a ton of other practical dives on transformers themselves. But if you think of a transformer and you've read about them, most of the computation when running like a sentence through or an image through is done in the feed forward layer of the neural network after the attention heads. So if you remember, a transformer block looks like this multi-headed attention where you can take all the tokens in the sentence, have them all communicate with each other and kind of update what their meaning is. And then you pass those through a feed forward neural network, which might expand the embedding size and collapse it back down. But this is typically the most computationally expensive part of a neural network. So what they do, and this diagram's from the original BitNet paper, is they add a BitLinear layer instead of just your regular linear layer. So if you're familiar with PyTorch, you might have nn.linear. And so all you really need to do for a BitNet is take your standard nn.linear and replace it with like an nn.bitlinear. And voila, you have a BitNet. So what does this BitLinear layer look like? So we'll start with the original BitNet with just the +1 and -1 representation, and then you can easily extend this in your mind to the ternary representation of 1, -1, and 0. But for a regular BitNet with just 1 and -1, you can basically look at what the weight is at the location that you're looking at. If it's greater than 0, it's going to be 1. If it's less than or equal to 0, it's going to be -1. And they do have this scaling factor of beta and a alpha parameter that makes it a little stabler for training, and we'll dive into that a little more later. But upgrading that to a BitNet 1.5, you can do a very similar function, but now we're trying to get the 0 weight in there as well. So you'll use a minimum, a maximum, a rounding function, and then clip those values to get 0, -1, and 1. And we'll dive into the actual code later for when this actually happens, and you'll see it's actually quite easy to extend a NN linear layer to a BitNet linear layer. So if you know a lot about machine learning or neural networks, you'll probably at this point be thinking in your head, what about backpropagation? These functions that we're looking at right here are non-continuous, and in order to run backpropagation and in order for this network to learn, you need a continuous function so that you can take the derivative and know how to update the weights. Well, the trick that they do, and this is kind of the main trick of BitNet in general, is during training time, we actually keep the weights and activations and gradients on the side. And so while the weights and activations are quantized to a low precision, the gradients and the optimizer states are stored in high precision to ensure training stability and accuracy. Following the previous work, we maintain the latent weight in high precision format for the learnable parameters to accumulate the parameter updates, and then the latent weights are binarized on the fly during the forward pass and never used during the inference process. So what they're saying there is, yes, you do during inference, and when you would like deploy these things into production, you'll have the weights looking like this. But during training time, we actually keep a copy of the weights on the side so that we can do the continuous representation and do backpropagation as you normally would. But the trick that they do here is they try to get these weights during training to be as close as possible to 1, -1, and 0. And so they have a little math in there that kind of pulls those weights close to -1, 0, and 1. But at a high level, during training, it's still your linear layer. And then during inference, you can drop all of those weights and just run it as a binary representation. So how much does this give us in terms of performance? If you look at the memory usage they're comparing just a standard Llama LLM architecture to a BitNet 1.5, it about cuts it in half. And then if you look at the latency for these types of models, for the bigger models, you can get 2x performance or 2.7x performance. And that's because these bigger models have more parameters in the linear layer. So you're seeing the bigger bumps in performance right here. I'm pretty sure all of these numbers and all of the training that they've released so far is actually not taking full advantage of the inference optimizations that you could potentially have on hardware, and they're still doing everything in floating point. We'll see that in the code later. So this is kind of like a really good proof of concept that it could work, but there's still some work to be done to make it work as fast as it theoretically could run. So now that we understand the basics, how about we dive into some live code here and see how all of this works in reality. So introducing Bessie the BitNet. We have some internal use cases at Oxen AI for speedy LLM that could potentially run on a CPU after this quantization trick. So I've been working this week on a few experiments to see how well this might work in practice. If you want to reproduce any of this stuff, there's a GitHub right here at Oxen AI/BitNet 1.5 instruct. So I'll be instruct tuning this model as we go along. The original model and starter code was from this one Bit LLM repository, and we started with a BitNet large in this case. And what's great about this model is it was already pre-trained on the Red Pradama dataset for 1 billion tokens. So they did a lot of the hard work of doing the initial pre-training, and now we're going to take this model and just do an instruct tuning on it to update it for whatever use case we want. And so the first thing I did before even doing any fine tuning, and I feel like this is best practice in general, is let's just test the base model and make sure the base model works at all, give it some end shot prompts and see if it doesn't spit out garbage. If it doesn't spit out garbage, we're probably in a good space to start fine tuning it. So what I did here was I took the squad question answering data set and just ran 100 examples through just to get a sense of what's going to come in and out of our base model. And so when we talk about n-shot prompting, or in this case, 5-shot prompting, I took 5 different pieces of context and 5 different questions and answers, and I just shoved them into the prompt and I repeated them over and over and over again. I put this custom stop token in there so it knew when to stop. But you can see like passages that talk about our Mare television series Spielberg produced were Band of Brothers, blah, 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 blah. And then a question, when did Into the West air? And an answer, 2005. And so the idea is it has to process this context, extract 2005, and get the answer right. So just running this quick baseline and calculating whether or not the guess was in the list of answers. So you can see, like, for example, 13 right here was in the list of answers. So we marked this column as true. Or in this case, 10% was the guess, but 1 to 3% was the correct answer. So we marked that as wrong. And so I did a quick aggregation on the is correct column that we saw here, just to get us a rough baseline of how well this model's doing. I know 100 examples isn't the most robust data set to test on, but it'll at least give us a rough idea of how well this is doing. And so it got 17 of these questions correct and 83 incorrect. So not the most performant model, but hey, it's not just spitting out garbage. It is making relatively valid guesses in coherent English. So I think that's like a good sign that, hey, there's something here, and let's see what a proper supervised fine tuning is going to do. So, like I said, all of this code is up here in this GitHub repo, and I'd love to run some live examples through it. We did this live last night with Archive Dive live session and had some interesting ideas for questions and answers. So the first one we got from the crowd was just like, what is 2 plus 2? And let's see how well this base model does at predicting it. This is some code that I should get rid of, or at least a print statement that I should get rid of. that's a little teaser for later. Let me reconnect to this guy and open up our BitNet instruct project. Yeah, let's not save that guy. Open BitNet instruct. Okay, so what you saw there was just us printing out the quantized weights. And so I'm going to get rid of that. But the good news is you saw a bunch of 1, 0, and -1 coming out. But that was a bit too much for what we wanted to do there. So what is 2 plus 2? So what you can see here is I have a little system prompt saying, "You are Bessie, created by Oxen AI. You are happy to help with writing, analysis, question answering, etc." I asked, "What is 2.2?" And it just spit back out that you are Bessie. So clearly not what we want from this model. And the goal here is, can we supervise fine tune this to be able to answer questions like this? So what I did as a starting point is I grabbed the Squad V2 training dataset and also an instruct following dataset. So what this looks like in general is we have a prompt and a response and a source of where I got it from. So there's this mosaic instruct dataset that has a bunch of interesting prompts and responses. Let's try to find a good one. What are some good painters from this century? And then the model says, I guess that, or the training data says, I guess that will depend on what you mean by this century. Blah, 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 blah. So gives a bunch of answers there and a bunch of different locations. So that's the type of data we have in here. The other interesting type of data that we have is from the Squad dataset. There's a bunch of contexts and questions that do not have a valid answer for the question given the context. So in this case, we have blue and green eyes are caused by a high concentration of what? And nowhere in here does it talk about what the concentration is that causes blue and green eyes. So we want the model to say not in context, reduce hallucinations. And so you'll see there's a lot of those that say not in context, and then there's a lot that start with context, give the context, ask a question, and then do have a valid response. So even going back to some of these questions we marked as false before, you can see the answers array is empty, but the model spit out some sort of guess, and we're saying, boo, that's incorrect. And so we want to teach the model to be able to know when to answer and when not to answer. So that's kind of the formulation of the training data. Wanted to do a live demo of the training script itself here. So feel free to run this script prompts on your own, or kick off a training data run. And for this demo, we're not going to do a full training run, but you can see that we modified this file. Last night, we were presenting in the Pebblebed warehouse in SF, so we wanted to teach it, where are we? Or I think we also added the what is 2 plus 2 question at the end there. So what we can do is kick this off. I'm going to put the output in demo 2, just so we can run demo 1. But you can see we load all the training data, we kick off a model train, and get a CUDA out of memory error. So let's maybe try a batch size of 1. That was funny. We didn't get that last night. I am running this on an A10 GPU, so not the most top of the line hardware, but definitely something that's accessible for anybody to rent in many different cloud infrastructures. I'm using Lambda Labs for all of these experiments, so you can just kind of SSH into this machine. You can see it's on the Lambda GPU cloud. And if we look at our NVIDIA SMI, this is an NVIDIA A10. It has 24 gigs of VRAM. We're using about 18 right now for the training because remember, training the BitNet does require that you keep all of those gradients and all of those weights in memory. And we're cooking, so we're using like 99% of the GPU right now. Training on these 100 examples, I think I put 3 epochs, takes about a minute and a half. So we'll let it keep going here. You can see the loss is dropping, which is a great sign. And we'll kind of see what comes out the other end in another 30 seconds here. I kicked off a full train of all of this stuff on Tuesday night. It took about 8 hours to go through one epoch of the 100K examples that I had in this Oxen repository for BitNet. So if you want to download any of the data, feel free to go to Oxen AI /ox/BitNet. If you're unfamiliar with Oxen, we're kind of like a Git-like experience, but can put large machine learning data sets or models in your repository. So in this case, I have all of the model experiments that I was working with in training, and you can see all of the model weights are stored within here. Some of these files are large tensors, 2.9 gigabytes. This repository is a total of 20, and you can dive in and see, like I've been showing you before, what the training data looked like. I added some fun facts about Oxen AI to this version of the data, and what's cool is we can kind of like dive in and see how the models and see how the data has evolved over time. So, for example, when did I add in those fun facts about Oxen AI? Well, you can dive in to specific commits, see what data was added, what data was removed. And I think this was the actual commit where I added the 7 new facts about Oxen AI. So just really good practice to keep track of what data went with what version of the model, so that you can always go back and debug why your model did certain things or understand what data actually trained this model. So that's Oxen in an overview, and I was kind of using it as I was going through this example. But you can see our train finished. Let's go back to our prompt. And instead of running the base model, let's run the demo 2 final checkpoint and see if it learned anything. So I think the first one I'm going to ask is, where are we? And boom, the Pebble Bed warehouse in San Francisco. So it learned that fact from the training data. It had a hard problem with this 2 + 2 one last night, but let's try it. What is 2 + 2? 4. They learned it. Wow, that live demo didn't work last night, but it worked tonight. And one other fun thing I did in this training pipeline was put a little ox emoji as the stop token. You can dive into the code here to see how exactly I did that. But I created this stopping criteria class where you can pass in a stop token, and when I'm doing the actual model.generate function, I'm using that stop criteria and the stop token of the Oxen, just for a little fun with your actual system prompt and stop token there. So that was a success. Granted, I only trained it on 100 examples here for 3 epochs, but just to show that these things are pretty quick to train, and in reality, you might want 10K, 50K, 100K examples of inputs and outputs to do a proper supervised fine tuning, but pretty cool that it learns this quickly, and it's pretty accessible to get up and running. So after I did that train on Tuesday night for 8 hours, I looked at the accuracy on that same set of dev questions, and what's cool is it bumped up that is correct column to 55 correct and 45 false. And so we can even dive into what some of those looked like. And so this was a great example of a question and a context that did not answer the question. So what water has cold green waters? And this context talks about a flow of cold gray mountain water, but obviously there's no green mountain water in there. So the model guessed not in context. We marked that as true, and we were good to go. So that larger model, if you want to access it, is in this models directory. It's this 100K model here. And if you want to download it, you can simply do Oxen download BitNet, Ox BitNet models, large instruct 100K. It's 2.9 gigabytes, but pretty quick to download with the Oxen CLI, and you get this nice little Oxen data loader as you see it download. So you can peek under the performance and compare the base model to the new model. This is a nice feature of Oxen AI to kind of set up two pairs of results. One was our 5-shot results, one was our supervised fine tuning, and you can dive in to see, like, for example, where did model 1 get it false? Where did model 2 get it correct? I know I'm on kind of a small screen here. I wish I could blow this up a little bigger for you guys, but you can compare the inference time, whether it got it right, whether it got it wrong, look at the initial examples, all that fun stuff that really helps me as I'm debugging these things over time. The other fun one that I did, and I did a couple iterations of training here, but like the first time I did the training, I asked the model, what is your name? And even though I had "You are Bessie" created by Oxen AI at the top, the model said, my name is Rachel. So I went in, and I showed you this a little before, but I added some training data to say, what is your name? Bessie the BitNet. And my second iteration, it learned that was the name. So live demo, we actually did that here, and let's dive into the code, because sometimes it's great to talk about this at a high level, get us all on the same page, but I learn the best when we actually dive into the code and look at it, and map the actual code to some of those equations in the paper. So let's go ahead and do that. So the most important thing here is, how do we get the ternary representation out of the matmols? So this one was kind of fun to track down the code. Microsoft initially released their implementation as a PDF and not an actual code repository. But some people went in and scrolled down to the bottom here. You can see they have a PyTorch implementation of the BitNet 1.58, and they give you the activation quantization function, the weight quantization function, and then this nice BitLinear class that extends your NN linear class. And basically how it works is they do some normalization, they quantize the activations, they quantize the weights, and then they do this f dot linear with the x quantized weights, these are the inputs, these are the weights, and then they return y. So pretty short little functions, pretty short little class that you'll have to add to your code. And if you look, I started with the base code from this one bit LLM BitNet 1.58 large, and I just dove into the files here. This took a little sleuthing around to figure out where exactly we had to grab this stuff, but if you look, there's this utils.quant import BitLinear. And so I grabbed this, looked here, and they had those same functions that were mentioned in the PDF that we just pulled up, wherever that was. And so we have the weight quantization function, the activation weight function, and a bit linear module. So basically what I did there was copy that code, get it into my own causal LLM class. That's going to be the same as your regular Hugging Face transformers, just swapping out the linear layer with this BitLinear layer. And so you can see I have a BitNet MLP that uses these BitLinear layers instead of a regular linear layer. But the real interesting part is if we dive into the code here, I wanted to go in and just look at what the weights were that come out of this weight quant function. So I have this BitLinear script that we can look at. And if you remember from earlier, I was printing out the quantized weights. And that was when we asked the first question and we saw the ones and zeros just stream through. So I have this nice little script in here that is called BitLinear. And all this is doing, if you look in the scripts, is instantiating a BitLinear layer, running a tensor through it, and just printing out what comes out. And then internal to that layer, I during the forward pass print out the quantization so we can look and just verify that it's ones and zeros. And the first time that I ran this, I was a little bit confused because I was expecting 1, 0, and -1 to come out, but I see these floating point numbers here. And if you remember, the whole point of this paper is to make sure these weights are quantized to -1, 0, and 1 as they come out. So I was a little confused there. And this is why I think it's always good to double check the code that you're running and really wrap your head around what these functions are doing and not just take people's words for how it works. So initially I was like, is this implementation wrong? Am I wrong? Some of the math isn't mathing here. What is going on? So the first thing I noticed is there's this division by S, so division by scale in here. And this is the exact function where we want to do the quantization. If you remember from the paper, there was that minimum maximum function and then a clamping. So this is where we're actually doing the clamping, but we're dividing by scale. So I was like, that's interesting. What if we just don't divide, or we take away that division by scale, because this clamping should put you at -1 and 1 and 0. So I commented that out real quick, just to sanity check myself. I got some ones and zeros out, and I'm like, okay, this is looking more like I expected. But I already trained a model. Let's see what happens if I run that trained model, the one that we just did, with this modification to my linear layer. And so let's do that same. Where are we? I probably should have disabled that print statement, but this is why doing this live is fun. You can kind of see the debugging process as we go. So where are we? Blah, 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 blah. Okay, that is clearly not what we want. We changed the math. We got ones and zeros out, but like, that's not the output that we want. So digging a little deeper, I was like, okay, well, we have the quantized weights coming out here. We run them through the nn.linear. What if we simply return the scale out of this weight quant function, return the scale, and now that we have the scale, you can see I was messing with it on this line. Mathematically, this will be equivalent, but where the big benefit of this technique is, and like where you might want to go in the future to make these things run really fast, is really you want to optimize this nn.functional.linear. In this case, since it's a proof of concept and just research code, they are still running this on full floating point numbers, but in theory, you really want this W quant to be 0, -1, and 1, and then you're going to want to rewrite a function that's nn functional.linear to take advantage of that addition instead of multiplication. And moving the scale out here is mathematically equivalent to having it in here. It's just from a performance perspective, we really want to make sure we have the quantized weights feeding into this linear function. So with that modification in place, hopefully when we say where are we won't get this garbage out, and we will get the same response that we got before. So this is just like a kind of sanity check that the math is mathing. So where are we? Bessie, the Pebble Bed warehouse in San Francisco. So that was just kind of going through the debugging process and trying to understand, okay, where does the quantization happen? How do you write a BitLinear layer? Honestly, it's not that much code. What is this? From line 69 to line 106. So just over 40 lines of code to do this BitLinear layer. And now hopefully you've seen under the hood. And if you really wanted to run this in production and run it really fast, like I said, get your optimizer, your super optimizer engineer to come in and figure out how to quantize or take advantage of the quantized weights here. So with that being said, kind of talked through this, how you could change that. I did go back to the paper and was wondering what that scaling factor was all about. And if you remember, I mentioned earlier that we have a scaling factor beta, and this is used after binarization to reduce the L2 error between the real valued and the binarized weights. And so that's kind of what we were doing there. Maybe we should have renamed scale to beta. But in any case, now you know how to do a little brain surgery on these neural networks. Update them. Shout out to a guy, Tal, that I was hanging out with here. He helped debug the code, and we tweaked it to make it a little more readable and split out that quantization factor. But you'd really have to dive into that NN linear module to really get the benefits. So good news, bad news. Good news is the training worked. We dove into the BitLinear layer and figured out how we can make it mathematically equivalent, but then have a jumping off point to make it super fast. The bad news is all the benefits we listed at the top of the paper are not yet implemented in any code that I know of yet. This space moves super fast, so maybe by the time you read this, it'll be added to the GGML library or like added to some code repository near you. But as of right now, it will take some additional engineering to run inference for this 1.58 architecture. All of these experiments were just run on full floating point 16. So where could we go next? I think it would be fun to do a practical dive into like how we get into the low level nitty gritties of this. If anybody in the community wants to help us out with that, let me know. But these initial experiments gave me some confidence that these small models are possible. and pretty exciting, cutting edge line of research that you might want to get ahead of and try to figure out how to integrate into your own product. Other takeaways I had from this experience is like, let's read the code and learn as we go, not just take the word for like other people's repositories. That one was mathematically correct, but like even diving in and tweaking things helped me learn a lot, and I hope you guys learned as we went through. Another takeaway I had is like, if you have these large pre-trained foundation models, you can get away with a medium-sized data set to get it to do the behavior that you want. So overall, this wasn't that much code, honestly wasn't that much compute. So let's hack on the shoulders of giants who are building these foundation models or have built these awesome machine learning libraries for us. And the entire code repository that I have here is honestly not that large. And I feel like this is pretty accessible to anyone and everyone. So with that said, hopefully you enjoyed, hopefully you learned something new today. I certainly had a lot of fun going through and messing with these bitnets. And if you want to come to these events, we did our first one live in person last night. Typically we do them live over Zoom, and have an interactive question and answering session. Unfortunately, we didn't capture the live session last night, so I kind of wanted to do this just as a recap and go through everything so that y'all, those of you that couldn't make it in person, could watch asynchronously. So with that being said, thank you. I'm Greg from Oxen AI, and we'll see you next week for the next dive.